Hi, welcome to lecture 6. We're going to talk about particle propagation and causality today. And first, let's begin by discussing a little bit the time evolution. Overall, our prescription was to build quantum fields. It's basically taking many oscillators in each point of space and replacing the numbering index I by the space-time, by the spatial coordinate x. For the time evolution, it is also better to have the time evolution in the operators. Now remember the quantum mechanics, and there are two different pictures. One is the Schrödinger picture where the states evolve and they follow the Schrödinger equation where the time derivative of the state is governed by the Hamilton operator acting on the state. And so the solution to this equation gives you how the wave function on the state evolves. Here, the operators of space and momentum are constant quantities. Then there's the Heisenberg picture, where the operators evolve and the states are constant. The pictures are completely equivalent, and we can show that by introducing a unitary time evolution operator defined by this equation. The derivative of the operator times I is given by the Hamilton operator acting on this operator U. Now, if the Hamilton is constant, which it often is, the equation can be integrated and U is just the exponential to the negative IHT, where the H is the Hamiltonian operator defined in the appropriate way. And this state in the Heisenberg picture is then defined by U dagger applied to the state in the Schrödinger picture. And the operators in the Heisenberg pictures are sandwiches between of operators in the Schrödinger picture in between the U dagger U time evolution operators. We can show that by this prescription, our equations, the defining equations of the quantum theory are unchanged. For example, the commutators, if you write them out, we can pull out U and U dagger. The commutator is just a number. So U and U dagger meet each other, and U and U dagger are unitary, so their product in this way gives 1. We can also see it that the unitarity of this operator follows from the fact that the H is Hermitian, and it must be Hermitian because it measures energy which is unobservable. Similarly, expectation values are conserved. If you write it down in the Schrödinger picture, then insert the U dagger operators switching to the Heisenberg picture. We just see that it's redefining the notion of what is the state and what is the operator, and then the observable, which is the expectation value, is unchanged. Finally, we can derive from there that the time evolution of the operators in the Heisenberg picture is just given by the commutator with the Hamilton operator. That's a nice feature we can exploit. Finally, we can prove and furthermore use the fact that the annihilation and creation operators sandwiched between U and U dagger are just mapped to themselves times exponential function with the energy. This is the consequence of the consequence of this is the fact that the computation relations of H and A just bring down the energy with the negative sign for annihilation operator and with the positive sign for a creation operator. Remember that this is really analogous to the case of the normal standard quantum mechanical harmonic oscillator, where we had omega, the frequency here, which essentially measures energy of the oscillator. Here the E measures the energy of the mode with the momentum P. So we see that the way we introduced and set up our fields, phi, is actually, we set them up as operators in the Heisenberg picture. To see that, we can write this field as a function of x and t, right, as we defined it, and then split these exponential functions with the 4 momentum products, multiplying the 4 vector in space-time, in the piece which has the time evolution explicitly, in the piece that has the spatial Euclidean products of the momentum vectors and the spatial coordinate. Now we note that those combinations here, or the a and dagger and a multiplying the exponential function with the e, can be written as the operator sandwiched in between the exponential functions with the Hamiltonian. We can pull those functions out after we write the equation, and those functions are just the unitary operators that drive this time evolution. So this operator is the Heisenberg picture operator as we defined it above, with the Schrödinger picture operator is just this field without the explicit time dependence, where we just have the integral over the spatial momenta, and the exponentials only have the Euclidean products. We will use this notion to explicitly demonstrate that certain quantities are actually Lorentz invariant. Now, let's come to causality. The commutation relation we have introduced so far are actually evaluated at equal times. So for example, this phi and the momentum of phi commute to give you a delta function only when the times are equal. But in order for the theory to be causal, to preserve like ordering of events, we need that any commutator of field operators vanishes if we evaluate it at space-like distances. That means that an event that is lying outside the light cone cannot influence an event which is inside the light cone. This is just a mathematical way of writing it. Yeah. So if operators commute in a quantum field theory and in general in quantum theory, they do not affect each other. They're independent. So we have to require, in principle, we could require this as an axiom when we build the theory, but in fact, the way we have constructed the theory, we can check that this is indeed the case. Let us do that by defining this quantity here, which is the commutator of two field values, or just the simplest field operators, just the fields themselves, evaluated at space-time points x and y. Just simply substituting the definition, the composition of phi, we can write everything out, group terms, see which terms cancel and which terms give us combine to give us delta functions. Those two are give the commutator of a and a dagger, and these two give you the commutator of a dagger a, so we get the minus sign here. So we get this red delta function from here and the green delta function from the other combination that allows us to execute one of these integrals and evaluate this integral and sets q equals to p. Yeah, so these delta functions are gone and those exponentials are simplified to have px minus y, and again px minus y, just here we have a minus sign in front. And those square roots can be simplified to just give you 1 on 2 EP. Now, we see a couple of things now. So we started with a commutator of operators, and in this case, we can really show that this is just a number. Yeah? In principle, this is just a complex number. So that is an interesting observation. And another thing is that we manifestly see that this is Lorentz invariant. We have proven previously that this measure here is Lorentz invariant. And those products are 4-vector products, p times the difference of space-time vectors, but this is a Lorentz invariant scalar product. So this whole expression here is invariant under any coordinate transformation. So explicitly written like this, yeah, we know that this quantity is Lorentz invariant, and now we can do a couple of checks. Let's take, for example, x minus y at space-time vectors is purely time-like. So the spatial separation is 0. There are no entries here. There's time component. You would get it by setting this vector to be like 0, 0, 0, 0, okay, and this vector to be t 0, 0, 0, 0. So that's why the difference is just t0, 0, 0. Now, if we do that, we get, putting it in this expression, we get um, the argument here, the difference of the exponential, is just collapses to e to the minus et minus e to the iet. Yeah, so this is a combination which doesn't vanish in general. Okay, but it shouldn't. You have a time-like separation. The commutator is a value, is a number. It's fine. The events can influence each other. They are inside the light cone. That checks out. What happens now if x minus y squared, the norm, this the Minkowski norm is negative? In other words, that the events are space-like separated. We can take an example, setting times to be equal, but the spatial coordinates to be separated. And we get negative sign from the metric in here, and the square, so the Minkowski square of those two vectors could be negative. Putting it explicitly in the expression here, we see that writing it out, we have the time part that vanishes, and we have those two exponents with p multiplying the difference in x and y. The sign here is different, but p is just a dummy variable, so we could in principle take the integral applied to this first, and then also take the integral applied to that second, because this integral is just a sum and we can split it. Since p is a dummy variable, in the second integral we are free to flip the sign of p, and we will get the same term here. So there are two integrals that are exactly identical, and this expression is identically zero. Now, since the whole expression is Lorentz invariant and it vanishes for this particular time-like vector, it vanishes for all for this time-like space-like vector, it vanishes for all space-like vectors where the product signature is negative. This is what we want. This is really shows us that this commutator of fields preserves causality. Let's see again as a picture in the 1 plus 1 dimensional space. If we have here the space, here's time. This point here, for example, is inside the light cone of this, or these 2 points are inside the light cone such that they can influence each other, and their commutator would not vanish as we checked before. And those 2 fields are outside the light cone, from each separated from the light cone from each other, and their commutator vanishes. So they are not talking to each other. These 2 space-time events will not influence each other. So the commutator of the fields preserves causality. Has a well-defined causal structure. And this is really great. This is what we really need from our theory. In the next lecture, we will talk about particle propagation and how the quantum field theory structure ensures that, in fact, the field commutators vanish. This has to do with the way particles propagate in quantum field theory.